Let's go to worksheet. So this is problem number 4. Problem number 4 is the one we will focus on. Okay, I'm going to do A through D. If you want to do the rest of it, I would recommend that you do the rest of it because it's got some extra credit quality implication. That problem has that implication. All right, so what do we know? So we got a person jumping in front of a train. The train is moving at 60 miles per hour, right? All right, so the train is moving at 60 miles per hour. The amount of force acting on the person is going to be 375,000 newtons in the direction of motion. All right, so a couple of things, figure out the acceleration of the person, so we're interested in, and then the train, and then figure out the speed of the person as well as the train after impact. Okay, so what do we know? A couple of things we know. If the train is moving at 60 miles per hour, upon impact, we expect the person to move at double the speed of the train. So if the mathematics, if Newton's laws are correct, they should agree with what we expect, and what we expect is what we're able to measure. All right, so if the train is going at 60, person should be moving about 120. It's going to be slightly less, but more or less. Nevertheless, it's going to be about 120. Train speed is not going to change that much. It's still going to be about 60 miles per hour. It's probably going to be about 59.999. So that's what I expect to see. So that's what we got. All right. That's what I think is going to happen. All right. So what I'm going to do, I'm going to just cheat. Just grab this. Okay. So these are the formulas that I'm going to be using. I'm going to take those into the worksheet. All right. So I'll just to the side. Just want to make room. All right, so those are the formulas. That'll be useful. All right, so the force is going to be responsible for, the force is going to be generated in impact, so it's going to be responsible for the acceleration. During impact, the acceleration is going to change because you're going to be looking at broken bones, this and that, so it's going to be a chaotic motion, so average acceleration formula is going to be available for use in this problem. All right, so the first thing I'm going to do is I'm just going to list everything. All right, so I'm going to have the person here. Okay, so let's just go here. And I'm going to have the train here. All right, so what do we know? I know that the mass of the person is going to be 70. It says 70 kilograms. So that's the person's mass, and the train's mass is going to be 3 million. All right, so I got 70 kilograms here. And the train is going to be 3 million. All right, what else do I know? I know that the train is moving initially at 60 miles per hour. All right, so we got 60 here. So that's the speed of the train. So the train has an initial speed. And I also know that the person is not moving, so this is going to be 0. Person is not moving in the direction of motion. All right, so the train is moving, not the person. Okay, what else do we know? They will share an impact time. And this is 100th of a second impact time. All right, so what do we do? A and B, figure out the accelerations for the person and the train. So I want to know what these accelerations are. And for safety reasons, I'm going to express the acceleration in terms of g. And then let's figure out the speed of the person and the train right after impact. So what is the final speed? And obviously, it makes sense to express them in terms of miles per hour because that's what we can relate to. All right, so we have only one single conversion, 60 miles per hour to meters per second. All right, so 26.78 or 79 meters per second is 60 miles per hour. That's it. All right, so find the person's acceleration as well as find the train's acceleration. Okay, so what do we have? Guys, this case is simple. Train hitting a person. You got the train, you got the person getting hit. So action force is going to be acting on the person. Reaction force is going to be acting on the train. It's going to be in the opposite direction. Acceleration is going to be caused by the action force acting on the person and the reaction force acting on the train. All right. Either way, acceleration is going to be caused by a force, action and reaction forces. So force is going to be responsible for the acceleration. So acceleration is the same as force divided by mass. That's it. That's as far as this is going to go. All right, so what do we have for the person? A. All right, so the acceleration of the person is going to experience the impact force. All right, we don't have the impact force, so I just copy down the impact force. Action and reaction forces is going to be the same. It's going to be 375,000 newtons. All right, so we got it. So the action force is acting on the person. It's going to be positive divided by the mass of the person. All right, so what do you get for this one? Give me the number.
$5,357.14.
5,357.14 meters per second squared. Give yourself 5 points. Okay, I'm going to just move the decimal to the left. All right, so this is about 500 Gs. All right, guys, this is dead upon impact. In reality, the impact time is going to be shorter than this, but this is dead upon impact. Okay, so that's the acceleration of the person. What do we expect to see if we're getting the train? All right, so the reaction force is going to act on the train. All right, so it's exactly the same force, except it's going to be in the opposite direction. And it's going to be acting on a mass which is 300 million. All right, so what do we get here?
$0.12.
Negative.
All right, so it's going to be 0.12 in the negative. This is very small. I don't need to convert this to a G. It's meaningless. This is way too small. Okay, so I'm not going to even bother with that. All right, give yourself 5 points for that one. Okay, good. For those of you guys who came up with that number, give yourself 5 points. All right, so C and D. So what is the speed for C and D? Okay, so what do we know? We know that this is impact. What do we expect in impact normally? In impact, we expect the acceleration to change. So, which means that we will get to use the average acceleration formula. All right, this, because we're estimating, we're trying to come up with an estimate for the acceleration. All right, so figure out the final speed based upon that. So I'm going to move my unknown to the left-hand side. And then just get rid of t. And then I'm going to add VO to both sides, so which means that I'm going to end up moving it to the right. So the final speed is going to be the same as the initial speed plus acceleration times time. Okay, so that's as far as we will go with this. All right. Part C, let's figure out the speed of the person. Okay, so what do we know? The initial speed of the person was 0. All right, so this is going to be 0. What that means is this person has an acceleration. What's the acceleration? The acceleration of this person is going to be 5,357.14. And the impact time, the duration of the impact is going to be 100th of a second. So the duration of the impact is here. Acceleration of this person is here. So you got to multiply those two. Is it 2/10? This is 100th of a second. Okay. So what do we get? This is going to be 1, 2. All right, so we end up getting 53.57 meters per second, right? Okay, convert this to miles per hour. And when you convert it to miles per hour, what do you get? All right, Lucy, give yourself 5 points for that one. Jack's same. All right, so multiply by, okay, very good. This is 119.99 miles per hour. All right, so Jack, give yourself 5 points for that one. So roughly 120. It's slightly under it. In real life, it's going to be almost 118 is probably where it's going to be. There's a reason for it, as you will find out. So what do we expect to see when it comes to the train? All right, so here's what we will see when it comes to the train. We expect about 60 miles per hour. Let's check to see if that's the case. Expect about 60 miles per hour. So D is going to be the train. So let's do the train. So what do we know? Train is going to have an initial speed. Remember the initial speed of the train. That was 60 miles per hour. So this is 26.78 meters per second. Just a reminder. Okay, so I want to make sure when we are looking at these formulas, in essence, we're using the same formula for both of them. But remember, guys, the train is going to have a negative acceleration. All right, so the train's acceleration is negative. All right, so that's going to subtract from the speed. All right, so our initial speed is going to be 26.78 plus we have a negative acceleration, which is 0.12. times a very small impact time. Okay, so this term is going to get subtracted from that term. Okay, so I'm just guessing right now. Okay, but there's going to be a very small subtraction. So this is going to be 26.70, 779. Okay, just give me the number. What do you have?
5.
Okay, it's going to be
So
77.
26.75.
Say it again.
26.75.
75. Okay, not bad. All right, give yourself 5 points for that one. Okay, so just convert it to miles per hour. And then when you convert it to miles per hour, what do you get? Okay, so you end up getting, yeah, that's good. Lucy says 59.98. 59.98, roughly about 60 miles per hour, right? Okay, notice that it works out. Okay, so Newton's laws work in terms of explaining it. Okay, so it actually agrees with what we expect. In that sense, you expect the train speed is not going to change, and it doesn't. And you expect the people to move almost double the speed of the train. All right, so which means that the person do apply the same force back on the train. Except the train is just so much more massive, incredibly massive, that the acceleration of the train is unnoticeably small. So that's what happens. All right, so what do we expect? Person getting hit by a train. You're gonna apply the same force back on the train, but because the train is so much more massive than the person who's getting hit, despite the fact that the forces are the same, because of the mass is so large that the acceleration of the train is going to be unnoticeably small. So head-on collision between a car and SUV, which one is going to experience a large impact force? It's going to be the same, right, for both of them. Except because the mass of the car is so much smaller than the mass of the SUV, the acceleration of the car is going to be much bigger. So which means that the car is going to suffer a lot more damage than the SUV. That's what it